This program is a continuation of nucleophilic substitution and a comparison between what's SN1 and SN2 substitution. First off, to understand when it occurs, we need to understand something about the halogenoalkanes involved. If it's a primary halogenoalkane, I can tell this one is primary because the carbon to which the chlorine is attached to just one over their R group. They undergo what's called SN2 substitution. If, however, that carbon is attached to three other groups, it's a tertiary carbon, and that would then lead to what's called SN1 substitution. The middle one, secondary halogenoalkanes, they could undergo either one of them, depending on conditions and the type of halogenoalkane and the type of nucleophile that's attacking. Let's begin by looking at a primary halogenoalkane. It reacts in one single step with a collision between the nucleophile and the halogenoalkane. So here I'll bring in my nucleophile. I'll use hydroxide as my example. Its pair of electrons would move towards that positively charged carbon. It can only attack from this side that I've shown because coming in from the right-hand side, the chlorine would be in the way. Chlorine, possessing a slightly negative charge, would repel the hydroxide, so it must approach from the left. The bond between the carbon and the chlorine is broken as well, as the two electrons from there will now join the chlorine. Partway to getting to my products, I form what's called the transition state, where there's somewhat of a covalent bond beginning to form between the hydroxide and the carbon-chlorine bond is starting to weaken. Ultimately, I end up with the following product. As I mentioned, this reaction occurs with the collision of a nucleophile and a halogenoalkane. That would mean that this reaction is second order, involving one of each. Being that it's a two-body collision, we call it a bimolecular process. Hence, that's why it's called an SN2 substitution reaction. Now let's look at what happens in the tertiary case. This occurs by two steps, and the first step is the slowest. The first step begins with the breaking of the bond between the carbon and the chlorine. There's none of my nucleophile required for this step. That step then results in the following formation. I form what's called a carbocation, where I have a carbon possessing a full positive charge. The shape of my molecule is also changed from a tetrahedral to a trigonal planar arrangement. As mentioned, this is the first step and the slowest step in the reaction. I can therefore conclude that the rate then depends only on the concentration of the halogenoalkane. It's a first-order reaction involving one body breaking apart, a unimolecular process, hence we call it SN1. Now let's take a look at the next step, the attack now of the nucleophile. So as before, I'll use the hydroxide nucleophile. Now it could approach from the left-hand side, and if it did, I would get the following product. But equally, I could have had that hydroxide approaching from the right-hand side, in which case I would have got the product you now see on the right. These two are not exactly the same. They're actually mirror images of each other. This type of substitution leads to what we sometimes refer to as a mixture of stereoisomers, and we'll learn more about those in a subsequent program. So again, let's substitute some of the differences. First of all, who's involved? A tertiary halogenoalkane for SN1 and a primary for SN2. Remember that secondary could do one or the other, depending on some other factors. The slowest step in SN1 is a unimolecular process, the halogen leaving, whereas in SN2 it's a bimolecular process, where the two reactants collide. The reaction orders are 1 and 2 respectively. The number of steps involved, though, is different. 2 steps for the SN1 mechanism and 1 step for the SN2 mechanism. And generally speaking, the SN1 reaction mechanism is faster. There are some other factors that affect the speed of the reaction. For instance, the nucleophile itself. If it possesses a negative charge, it will generally react faster than a molecular nucleophile. And finally, the strength of the carbon-halogen bond. The stronger it is, the slower the reaction. Please don't hesitate to ask questions. Thanks for watching.